883. The EMF works out to 88.4 into 10 minus 3 volts. So millivolts. 88.4 millivolts. Okay. Imagine if you have a pacemaker or something like that, they probably don't let you have a, well, I don't know, they let you do an MRI. All right. A single turn circular loop of wire of radius 50 millimeter lies in a plane perpendicular to a spatially uniform magnetic field. During a 0.1 second time interval, the magnitude of the field increases uniformly from 200 to 300 millitesla. Determine the EMF induced in the loop. So the magnitude of the induced EMF. Yeah. So the final field is 300 millitesla and initial field is 200 millitesla. So 100 millitesla by 50 millimeters square. A millimeter is 10 minus 3 meters square divided by 0.1 second. So that's 10 minus 3, 10 minus 6, that's 10 minus 9 volts. 100 times pi into 50 square divided by 0.1. So that's 1,000, so that will make 10 minus 6, and then this is 2,500, 10 minus 3, so 2.5 times pi. Works out to 7.85 millivolts. Okay, so in part B, they ask you, so I'm going to draw the loop like that. The magnetic field is out of the sheet. And it's increasing. So what is the direction of the induced current? So it's increasing, you want to oppose that. Current induced is like, okay? Because that will produce a field into the sheet.
So the dots are away and
The
crosses
dots are
towards-
the dots are coming out. That's the initial field,
Okay.
and you want to produce a field inside. Yep.
I'm looking at the PDF online for the last question, 24, and you got a different answer than
Okay.
what you got.
All right.
And I think it's because on the PDF it says, or you're saying that the flux is equal to N times B times A, and there you only said it was times B times A, not 3324.
Oh, 50 turn. Okay. All right. So. So times 50. So the induced EMF is 4.4 volts. All right. So here's a few Lenz's law questions. Use Lenz's law to determine the direction of induced current in each case. So the field is coming out of the sheet. If you're moving it in this direction, the flux through this thing is decreasing, through this loop is decreasing. So you want to increase the flux, okay? You want to oppose that decrease. So the current, induced current will be like that. Okay. Induced current will produce a flux magnetic field outside.
I thought it was reversed for that case.
Okay, so flux is decreasing,
Mm-hmm.
so you want to produce a magnetic field like that
Okay.
to oppose the decrease. Okay, so this thing, it's like, so the magnetic field is coming out. This is horizontal, so the flux through this thing is zero. The flux is not changing. So there's no induced current in this case. In this case, you're coming from an empty region to a filled region. So in the transition, the flux is increasing. So you want to decrease the flux. So the induced current will be like that. Only while it's coming into that region. Once it's fully in this region, that induced current will go to zero. So the induced current will start once it starts touching this guy, and you'll have an induced current, and again the size will vary, and the induced current will go to zero there. This guy, the flux is increasing, so you have to decrease the flux. You got to produce a magnetic field into the sheet, so induced current is like that. In this case here, the magnetic field and the magnitude is decreasing. Okay, so you want to produce a field in this direction as B is decreasing. And so the induced current is like that. Again, in this case, this is moving horizontally. The flux is zero through it, and there won't be any induced current. Okay, so that's a good problem to think about. A coil of 1,000 turns encloses an area of 25 centimeters square. It's rotated in 0.01 seconds from a position where its plane is perpendicular to the Earth's magnetic field to where it's parallel to the field. If the strength of the field is that, what is the average EMF? So the average EMF okay, the only thing that is changing is B, so N so no. No, that's, so initially the flux is NBA and the final flux is zero. So area is 25 into 10 minus 4 meters square. And this change happened over 0.01 seconds. All right, so that's 10 to the minus 9, 10 to the minus 6. This is 10 to the minus 2, so 10 to the minus 4 volts. 6 times 25. That's 150. 15 into 10 to the minus 3 volts. Okay, so the induced EMS is 15 millivolts. So the rod shown in the figure is moving through a uniform field of magnitude 0.5 Tesla with a constant velocity of 8 meters per second. So that's roughly how fast a person can run. What is the potential difference between the ends of the rod? Yeah. So the potential difference is BLV. So 0.5 Tesla, 5 centimeters. Okay. So we'll make that 10 to the minus 3, 25 times 8, which is 200 millivolts. So if Usain Bolt grabs onto this and runs in a field like that, that's half a Tesla is the field in an MRI machine roughly. You're inducing millivolts. Okay, a 25 centimeter rod moves at 5 meters per second in a plane perpendicular to a magnetic field of strength 0.25 Tesla. Calculate the magnetic force on the electron in the rod. Okay, so if you have an electron like this, the force on this will be, okay, so velocity is like that, magnetic field is like that. On a positive charge, the force would be like this. On this negative charge, the force is in that direction. The force on the electron is in that direction. And the force on the electron is QV cross B. The magnitude of the force is, since Q and V are perpendicular to each other, is QVB. So the force on the electron will be and then it says the electric field in the rod So the electric field, the force on the electron is like that. The electric field is, well, what did I do wrong? This is the magnetic force on the electric field is like that. All right, the electric field is electric field times the length of the rod is the voltage. Okay. So the strength of the electric field is that. Okay. And the voltage in the rod is B times L times V. So the electric field in the rod is B times the speed at which the rod is moving. So, which is 0.25 Tesla times 5 meters per second. 1.25 volt per meter. Okay. The potential difference between the ends of the rod. So we'll make that 10 to the minus 4, 625 times 5. So 0.31. So 0.3 volts is the potential difference. And then what is the speed of the rod if the potential difference is 1 volt? So the greater the potential difference, the faster you need to move. Okay. So at 5 meters per second, you got a third of a volt. So you got to move at about 15 meters per second to get 1 volt. $16 meters per second. This says calculate the induced electric field in a 50-turn coil with a diameter of 15 centimeters that's placed in a spatially uniform magnetic field of magnitude 0.5 Tesla so that the face of the coil and the magnetic field are perpendicular to each other. This magnetic field is reduced to 0.0 in 0.1 seconds. Assume the magnetic field is cylindrically symmetric with respect to the central axis of the coil. Okay, the induced EMF is the line integral. Okay, and that's equal to minus d by dt of phi. Okay, as you're reducing the magnetic field, you want to induce a current such that you're producing a magnetic field in that direction. So the induced current is in this direction. That's the direction of the induced field, okay? As B is decreasing. And because of the symmetry, this is E dot E is constant, and this line integral is just E times 2 pi r, the radius of the coil, the circumference of the coil. And that's equal to, so now we have the direction, so all we need is the magnitude. Okay, so it's just change in magnetic field times the area of the field divided by change over time. E times 2 pi r equal to change in magnetic field pi r squared. So pi r cancels with one of them, you're left with r. So the electric field is change in magnetic field times r divided by 2 delta t. Okay, so if you have a uniform magnetic field, the further out you are, the greater the radius, the greater the electric field. That's because you have a lot of flux changing. Okay, so it's that. Okay, so the magnetic field went from 0.5 to 0 Tesla, so that was 0.5 Tesla. The radius is 7.5 centimeters. And this change happened over 0.1 seconds. Okay. So we'll make that 10 to the minus 3. Oh no, that's 10 to the minus 1. Yep. Mm-hmm.
Oh, the terms don't matter for this one either?
Yeah. The NBA finals are going on and I'm ignoring the end. The Spurs gotta love themselves last night, huh? They lost a 29-point lead.
That's crazy.
That's crazy.
I'll watch sports.
But you know that it's crazy, right?
I would never do that.
I'm telling you. All right, so this is, we'll make that 10 to the minus, well, okay, we'll make that 5, 10 to the minus 2. So 0.5 into 5 into 7.5 divided by 2 volts. Okay, so 10 volts. Oh, no, this is an electric field. Okay. The current I through a long solenoid with n turns per meter and radius r is changing with time as given by that. Calculate the induced electric field as a function of distance r from the central axis of the solenoid. these two problems are combined. Calculate the electric field induced both inside and outside the solenoid if the current is changing sinusoidally. Okay. So here's a solenoid. It induces a magnetic field inside like that. B is given by mu naught n I. So when the current changes, the magnetic field changes. And so you're inducing an electric field in this region. Okay? And radius r. So this guy, the radius of the solenoid is r. Okay. Now I'm going to draw a separate diagram. Okay. So now let's have a ring here of radius r, and there's the magnetic field. Okay. So, and as the magnetic field is increasing, if the magnetic field increases, then the induced EMF is such that the induced current is in this direction. So the induced electric field will be in that direction. Okay. So induced EMF is this line integral ds, so which is E times 2 pi r. Okay. And that's equal to change of flux. Yeah. So for R less than R, so as long as the ring is inside the solenoid, the area, all of the area of the ring matters. Okay, so electric field times 2 pi r equal to d by dt of mu naught n I. The magnetic field inside is that, pi r squared. Pi r cancels, you're left with r, and then the 2 over there. So for r less than r, the electric field is given by mu naught n I the 2 there, mu naught n r, and only I is changing with time, so di by dt. Okay. For r greater than r, the magnetic field is only in this area, and this is r. So E times, this is for r greater than r, 2 pi r equal to d by dt of mu naught I and pi r squared. Pi cancels, and so the electric field is, once you're outside the ring, the strength of the electric field is decreasing as 1/r. Okay, so that's what it's saying. Okay, so let me summarize this. Okay, what we're saying is, so inside a solenoid, you're changing the magnetic field by changing the current. Okay, if you have a ring inside, the induced electric field in the ring increases with R as long as you're within the solenoid. Once you come out of the solenoid, the electric field induced at this radius decreases with 1/r. Okay. So that's what we're saying. Everything else being the same. The current in a long solenoid of radius 3 centimeters is varied with time at a rate of 2 amperes per second. Okay, so di by dt is 2 amperes per second. A circular loop of wire radius 5 centimeter and resistance 2 ohms surrounds the solenoid. Find the electrical current induced in it. Okay, so here is the solenoid. Its radius is 3 centimeters. Five centimeters. Resistance is 2 ohms. So the EMF induced in this guy is, magnitude of the EMF induced is d by dt of B area, B times area. Okay. D by dt of B is mu naught Ni. Area is pi R solenoid. So the flux is only this area is relevant. Okay. R solenoid squared. Okay, they haven't given us n. They need to give us n in this problem. Okay, so you can assume n. We'll put n in, and then we'll put this, we'll calculate the EMF, and then you can calculate the current. Okay, so let's say let n be 1,000 turns per meter. Okay, so they haven't given n in the problem. We are assuming n. So in that case, the EMF induced is mu naught is 4 pi times 10 to the minus. Well, let me. The radius of the solenoid is 3 centimeters. And the rate of change of current is 2 amperes per second. So that's 10 to the minus 4. That kills that. And then 10 to the minus 8. So 10 to the minus 8. 4 pi square times 9 times 2. Okay, so 7 microvolts, and the current would be induced EMF over the resistance, and the resistance was 2 ohms. 7.5 into 10 minus 6 volts divided by 2 ohms, which would be 3.55 microamps. All right, one last problem. A flat square coil of 20 turns that has its side of length 15 centimeters rotating in a magnetic field of strength 0.05 Tesla. If the maximum EMF induced in the coil is 30 millivolts, what is the angular velocity? So here is the expression. There. You turn a coil, and the amplitude of the voltage is NAB times omega. Okay. E max to NBA, in keeping with the theme, omega. $30 millivolts, 20 turns, 0.05 Tesla. Okay, that's 10 to the minus 4, so that makes it 300. Yeah. So E max 300. What are the units for omega?
Radians per second.
Mm-hmm. So about a quarter of a turn a second. Okay. About 90 degrees or so.